Yeah, that works. Well, welcome and nice to meet you. I was just wondering how many of you are from academia and how many from industry? I heard something about 50-50.
Industry.
Industry, first
We
industry.
did industry hands up, eh?
Yeah, and academia. Okay, well, indeed, 50-50. And people other from, you never know. Well, welcome. I completely agree. It's nice to see the two worlds together, and I think it's really nice what MDENet achieves here. Well, not only in the UK, as you can see, but from the UK. And we're pretty much would like to have something like that in the Netherlands. So your idea of a network of networks, that sounds really interesting. I'm Machiel from Bijl. I'm from a company called Axini, which basically, was PhD research gone wild. I thought, well, it's actually a good idea, but I want to do it in practice. And then university said, well, it's pretty much solved, right? So just do it in practice. And we were like, I worked in industry 5 years before I started doing my PhD. And I thought, well, we don't have, well, the only type we have is an integer. So how are we going to do it? And then they said, well, it's infinite. So you can project anything on the internet, which theoretically is true, of course, but from a practical perspective, it's a bit harder. Then basically they said, well, if you think it's such a good idea, well, go do it. And at that day, I thought, well, that's pretty silly advice. The day after, I thought, well, actually not such a bad idea. And I talked with a couple of companies, and they said, well, if you're going to do real work again, as they called it, please come. And we basically started at a financial institution called Robeco. They do investment portfolio management. And they had a big system with something like 1,500 business rules that all influenced each other. And if they started testing it, they hit something like 150, and they were a bit like, we don't know if we tested it thoroughly enough. Yeah, and I've been doing this since 2007, 2008 from Axini. And the first couple of years, it was just really from a technology perspective, we were like, make the best tool. And then after, I think it was something like 2015, one of our clients, they said, are you still doing that? I mean, you already have it. You already had it for 10 years. I mean, but when are you going to listen to us, what we want? And we thought, that's strange advice. Yeah, but we did. And then actually what we did since 2015 was a lot more adapted to engineers, the people that have to work with it. Because what happened before was that some of the, let's say, the early adopters in the management said, well, this is cool, we're going to do it. And then it got with the engineers, and they said, wow, this language, you need to know mathematics, and you need to do all kinds of difficult stuff. How are we going to do this in practice? And so that's basically what we've been doing since 2015. And I have to say it was good advice. It really works. Today, I will talk to you about a case of one of our clients, ProRail. It's the Dutch Railways, and a big program, well, not only in the Netherlands, but in whole Europe, including the UK, is European Rail Traffic Management System. It's a new way of operating the rails. And for one of the components, ProRail immediately started using model-based testing. So it started with the modeling before the programming. And yeah, this is an experience report about it. First, I'll tell you a bit about ProRail, what they do, what ERTMS, basically from a high level, what it looks like. And then I'll ask you which parts you would like me to focus. Because I have more than enough sheets. So based on your reaction, I will focus on a couple of them. So in a nutshell, what happens is this. So it's a complex system in a complex environment. And ProRail applied MDD with MBT from the start of the project. So before code was written. Did it work? Because that is always one of the questions. People say, yeah, MBT is such a promising technology already for decades, but never works in practice. Well, yes, it works. That saved at least 5,000 hours of testing, so it's a quarter of the total project man-hour. And the project was ready half a year before the deadline. And I have to say that doesn't happen very often at ProRail. They have pretty complex systems, and quite often it's the other way around. One of the things was that that made it more interesting was that they decided to use the Skilled Agile framework. It's an agile way of working. And this was the first project. We were actually really happy with it, but because model-driven engineering and agile works really well, although the people at ProRail wondered, well, okay, should we still do model-driven engineering now that we do agile? We're like, yeah, of course. And they were, why? We're not agile, so it solves everything. And of course, we had just started for half a year, and then COVID also appeared. So we did a lot of stuff from home, and I think that actually helped in the sense that the models made things really precise. A lot of the discussions happened before the programming was happening. So, but it also did complicate things, of course. Well, I already talked about me. So what is ProRail? ProRail is the government organization that's responsible for the maintenance of the railways, for the allocation of rail capacity and controlling the rail traffic. And the third bullet is basically what the project is in. But this part is basically what they say. What they always laugh about the IT projects, because they say here, of course, this costs money, but whenever we do something with real infrastructure, that's where the big money is. So if they, as they say, if they have to dig a hole in the ground, that costs more than basically the entire IT budget. So the combination is, and now with the ERTMS, a lot of stuff in the network infrastructure will change, but also in the IT. Just some numbers. So there's a lot of stuff, assets on the track, signals, switches, tunnels, around 22,000 issues, calamities. So they have a lot of stuff to manage. And it's actually one of the people asked me, isn't this the biggest cyber physical system in the Netherlands? What do you think? Maybe also the same in the UK, by the way. I don't know.
Surely that's telecoms.
So I was going to say.
Yeah, telecoms. Telecoms is bigger. Yeah.
It's not part of.
Same ballpark, or?
Well, telecoms has these big exchanges and things like that, plus all the stuff on the ground, etc. Would say simple.
Yeah. I had never thought about it that way, because I was just looking at parts, and then I said, wow, it has all these. And there was someone from the Internet of Things community, and I said, oh, all these switches, they're operable remotely. They're, oh, interesting. Let's see. Tell what time do I have, by the way?
So it's coffee breaks planned to start at quarter past 10.
10:15. So basically half an hour. So I won't show you this, but they had they run into all kinds of interesting things. Like they had an incident a couple of weeks ago where basically a bus got stuck on a crossing, and it was literally split in two. Nobody was in there, so luckily also nobody was injured. But of course, then their whole system and the whole planning gets. The idea behind ERTMS. So right now there are signals next to the track. There's all kinds of stuff, and basically the driver operates everything, and there's no communication from the train to the operators. Well, there is some. They can always call. There's GSM, for example, but there's no basically communication between the systems. Oh, by the way, do I need to stand into the camera?
It should touch it.
Ah, okay, that's good. What will change? There will become these thingies between the tracks. They're called balises, and it's basically like a big NFC thing. The train runs over it. It catches the identifier of the balise, and then the train knows where it is, and it can communicate it back to the operator, and then they also know where the train is. And then the next step, the level 3, then there will also be communication back. So traffic control can, for example, say you're allowed to drive up to a certain balise that is up to your on your track. So it will, and then all the signals, everything besides the track will go away, and everything is operated digitally. So it's big. If they talk about digitization, this is really digitization. And then the communication will become on GSMR, but they're not talking about it because basically when they thought about this, that was really fast. But nowadays, of course, you can have faster communication.
Quick question.
Sure.
Does that mean that the train controller, so the train driver, if the system goes offline, doesn't have any redundant information anymore to drive the train?
Well, they thought about that. It's a good question. But basically, so what you get there, that's called a thing called a movement authority. So you get authority to drive up to a certain point.
Yeah.
And if you don't get any new information, then you basically stop there.
Yeah.
And so indeed, if the network goes down, all the traffic, but it's basically the same what is now the case.
Sure. Yeah.
By the way, if you have any questions, no problem to ask them in between. If we get too many, then I'll try to figure out how to still get to the end. So this is basically the central part of what we were also in the system that we were modeling. So trains communicating back to the traffic control and traffic control communicating back to the trains. And in the end, although nobody talks about this, but in the end, this should also make self-driving trains possible. But given that it's a regulated market, that will still take decades. So this is basically what your question. The driver gets to see to where they are allowed to go, and then the farther they go, or this part that goes down, and then the train stops if you have not had a renewal. And this is what the traffic control sees, so they see where all the trains are and how far they are allowed to go. And then if you combine them, so this system is called process lighting, traffic control. This is the train information. It goes via an RBC. This is basically the central safety system together with interlocking. So interlocking prevents all kinds of nasty things happening on the rail. And then the RBC radio, radio block center communicates the train position to process lighting, and then process lighting communicates back to the train. For example, how far they are allowed to go, or that they should immediately stop. Those kind of commands in the back of the. And this is actually also so here you see ATIS. This is a system that we're modeling. It communicates with ASTRIS, with process lighting, with the RBC. So there's a lot of communication going on. And when they were designing it, they had already had experience with building this system. And that turned out to be pretty difficult to build. So they thought, okay, now if we have to make a similar system, how are we going to make sure that this one is under our control and that it's reliable? So basically, that's the question to you. How would you test such a system if you had to do it?
Very carefully.
Any ideas? So maybe on a more abstract level, suppose you have a communicating system that communicates with several others, and it's not only API based, but also session based, and there's stuff going on. You probably have systems like that in your. Any ideas? There are no wrong answers. So
Well, you got to validate the basic functionality, right? That works, and then you've also got scenarios.
yeah.
So different scenarios, which is more complex kind of tests.
Yeah.
I don't know beyond that.
Yeah, one of the problems that they had here was, in order to really properly test it, they needed to have the environment. They needed to have all the other systems, and these are also constantly in development. So, and if you find errors in this integrated system, you're already pretty late in the process. So, how can we speed this up, or in scaled agile terms, shift left? How can we test? Basically, they wanted to test the system during development. So they basically use two techniques. Either do it on an integration test, or start writing simulators for all the components. But the thing with simulators is it starts out simple, but pretty quickly they're maybe not as complex, but pretty complex. And at first it only has good weather behavior, but then it has a bit of bad weather behavior, or it starts out as a tool such that you can give education on the system, and then, well, it becomes more and more complex. And that's why they were really keen on model-based testing, because we can, basically the model-based testing tool can play in the environment of the system. Or as some people in the management there say, it plays a digital twin of the environment. Well, it's not entirely, well, it depends maybe on your definition of digital twin. It's not really that it's digital, but it behaves like the environment. And I'll tell you how that works.
Behavioral twin.
Yeah, that's yeah. Oh, yeah. What are the parts that you're interested in? So I can tell you a bit more about Axini, what Axini model-based testing is. Probably you don't need to do that anyway, that you have a bit more of an idea. Talk about why it's so difficult, and more experience or lesson learned, or other topics that you're interested in. I know it's early in the morning and everybody's waking up, but lessons learned, yeah. Experience, okay. Other ideas, and I'll just ask questions in between.
You'll be covering the Axini language tomorrow, right?
Yeah. So that's. I also had some things prepared to show what the models look like and those kind of things. But that's easier tomorrow, because then I'm behind my own laptop and then I can show those easier. Basically, the two things that Bijl runs into is variability and connectivity. And this basically, they all blow up. This is I stole this one from Jan Tretmans, the subway. You want to eat all the subway sentences, you have many to go. If you only have one bread, 2 meats, 2 veggies, then it's 10 to the 5th of sentences. As you call it, I guess. And you have the same problem with and this thing is the one that's difficult in cyber-physical systems. You have all these communication going on, and there you have the same problem. It also is exponential. And of course, in practice, it's not, because programmers don't make all the mistakes everywhere. But there are many places where it can go wrong, and especially with communication in subtle places where it's difficult to find the problems. You want to shift left, and some of them I'll go cover more quickly. And what we see with clients quite often, if this is not working out the way you would like to, then you find out in integration, on test benches or on different, and then all of a sudden teams are starting to point at each other. You didn't understand the requirements. No, you didn't have and this is the place, if something like this happens, then it's interesting to see what can we do to push it back towards the team to prevent this integration from happening. And model-based testing is one of them, but there are more. It can be, for example, also be an architectural change, that you have a session-based communication protocol, but it could be that it's just a one direction protocol. If you say it's just a pub-sub protocol, that would already prevent a couple of integration. But of course, here we focus on the model. And why is MDD so interesting? Well, BDD as well, but I won't cover that, because they relate requirements, design, and testing. So they basically quite often there are requirements, or at a certain level, or in certain people's heads, but they are not related to the testing part. Of course, people say they are, and of course they get inspired by the requirements, but it's not really checked.
Brings that question.
Yeah. Sorry,
Go
go
back to your previous slide.
This one?
No, that one.
Yeah.
Where you've got it automates the test execution. How about where you derive your test from? The tests automatically generated.
Yeah, I'll come to that. in a
Okay.
couple, yeah. Yeah, so indeed, with BDD, you basically still have to program your test, and you basically have one trace.
Oh, right,
yeah.
okay. Yeah,
And the nice thing with behavioral driven design, and the nice thing with model based is that you get it automates the entire test process. You can also get the test case generation and execution with it. Well, MBT is a pretty overloaded term, but the way we use it, it automates the entire process.
Does it cover complete state space?
Well, theoretically it can, but practically, for a bit of an interesting system, there are too many test cases.
Yeah. Well, model coverage, decision coverage, I think it is, which they need for like DL178B.
Yeah, that you can get. Yeah.
Yeah, okay.
So we just keep track of the coverage and we can report on it. Whichever, basically
It's
whichever,
DC, yeah.
whichever one you like. Yeah, so that was basically more, where do we do this? We do this in finance, high tech, rail. So ProRail, the example here, but also electron microscope from Thermo Fisher or insurances from Achmea. So it's a pretty diverse group. And but basically the finance area more has this variability problem, not so much the communication, although more and more, because nowadays also portals in finance are there 24/7. They're online 24/7. This is a bit what models look like, but you will see more of that tomorrow. So there are ways to group sets of states, a bit like superstates. Here I show an example of an Internet of Things door. Starts in a closed state, you can open it, you can lock it, and if you have the wrong PIN code too many times, it will shut off. And already through it, you see detailed states. So modeling language has all kinds of concepts to group things, to reuse things. And then if you have the model on the left-hand side, you have the system. So in this case, the ATIS system. On the right-hand side, you need something to communicate with it, an adapter, just like with other. So on this side, for example, the top side is XML over HTTP, just web services. The bottom part is, I think, SCTP with a combination of XML, but also with encoded ETCS messages. So the ETCS is the railway standard messages. And then, yeah, the AI part is machine reasoning. So there is, but it's not machine learning because we want to approach it from an engineering perspective. We want to be sure that what we tested, what it is. But this is where, example, the coverage comes from, that we know how to read certain states with constraint solvers with those kind of techniques. And then the game becomes, it analyzes the model, it starts testing, it gets feedback, and we try to cover as many states, data points as possible. And in general, we do this on the fly. So not offline testing, but online testing, because with reactive systems, they always react differently than you expected. And that's the whole point. And that's also why it's so difficult to test them offline. But I know in the network systems, they also use, for example, TTCN3 kind of approaches. But there they really run into this problem. And then they sometimes say, okay, now we put the system in state A, I test for state A, and surprise, surprise, it reacts in state A, and put it in state B. So yes, it is possible to do, but what are you then testing? Are you testing the testing code, or are you testing the actual system? And this prevents it. This you can just test it the way you want it. Well, yeah, this is just a TomTom analogy, but that's more for management really likes it. Then they say, oh, okay. And I assume that you're beyond that. So what is so if you compare it, you have manual testing, you get pretty good test cases really quickly if you have a good domain expert. If you do BDD or scripting, you basically start programming your test cases and your test data, and you automate the execution and the outcome, which is nice. You can put it in a CI/CD. You can get continuous feedback, but for complex systems, you get a lot of them. you run into maintenance problems. And then with our approach, you make a model. This part is then covered. Of course, the modeling is non-trivial, as you all probably know. But you can also generate part of your specification for it. You could even generate code. Yeah, yeah. I won't go into that today. But indeed, if you look at the bigger MDE proposition, yeah.
So I think it is an interesting question, because when you were talking about the rail system at the beginning, and you were talking about how you tested one of those components,
Yeah,
but also other bits around, how integrated is the sort of modelling of those other components for their development with the modelling of those other components for providing simulators for this sort of testing?
yeah.
Ideally, you would want to use the same models for both, so that you ensure that you're representing the same system, just at different, I guess, granularity levels and
different levels of abstraction, but it's also where you get the interesting bits where you start to integrate all this together, as you pointed out, and that's how it becomes really messy.
Yeah. So we do this. Well, we also have talked with Rutger about this. So we are looking into, and for some we already combine the code generation with the model-based testing. But the problem is you don't want to have it from the same model, or if you want to have it from the same model, you need to have something to the checks on the model. But for example, we run models against each other, so that we say we have a requirements model and we have an implementation model, and we check whether the two are conform or are refinement or something like that. We also tried some model checking, which is difficult with the standard model checkers. But nowadays with the things like Z3, these kind of constraint solvers, I think that's also there's a group in France. I forgot how. Maybe you know it. Well, they are in the SMT solver. They use SMT solvers for model checking, and that looks pretty promising because they're really powerful in the data, and the data part is what blows up the traditional model checkers.
Well, what are you? When I was sort of like getting involved with this, the model checking, big problem was always the dynamic classes and creating the dynamic classes, because it was just an unbounded problem then. That was always the blocker. Is that what the Z3 deals with then?
Well, Z3 is just a constraint solver, so you basically give it a logical formula, but you encode your model check problem in a logical formula, and then it tries to find a path or a counterexample,
Okay,
or
you set the proposition to see whether it can.
yeah. And it's when we started with it, I was pretty skeptical, because people have been trying this for 20, 30 years. But it's also had a discussion with, so the Z3 started at the Microsoft Research. And I had a talk with Thomas Bijl, and it's pretty decent stuff. So it's, yeah. I wouldn't say, I don't know if it's really already industry grade, but it's very powerful. And it can do stuff that other tools nowadays cannot. Yeah. Let's see. Why am I telling this? Because this you need for the basically the experience. So what we did, we made a model. Basically, our models are specifications of the system. So it's based from how ATIS looks at the world. So here it has an interface definition here as well. It knows which messages are allowed to come in, which messages should go out. And so we can play the entire environment of ATIS. And that's also one of the experiences. If you have that, you can really find and prevent integration problems, because they virtually have no integration problems. And of course they do. It's never, testing is never complete, but you find a lot less than you normally have. And it really saves time, because the integration phase is a lot shorter. And I think you asked about how about the other components. So one of the things that Bijl is now doing is also testing this component, which is basically the same model. Monetary, it's a bit of an enriched model, because you now have to look at the other
You
side.
look at it from the different direction.
Exactly. Yeah. And this one is not there yet. it's being built as we speak, but they do have simulators for it. So now we basically first run against a simulator, where we find bugs, of course.
But would you be able to, once you have the model, or on the other way around, when for testing RBC, are you able to use the pretest that you have already to provide you with the contextual behavior that simulators?
Yeah, partially, but basically this, when you model ATIS, you only look at, okay, what can happen all the time from the RBC side. And it's not so much that you think about whether it's logically, does it logically make sense that RBC that gives that message, for example, at any
of
time.
course.
But because we tested, ATIS becomes really robust against it. And the other way around, then we of course need to know more about the internals here, what's happening there. So
You've really got to understand the interaction. It's not just about the actor in RBC, just triggering information. It's got to have actual behavior in it. And reactive behavior.
Yeah, and one of the lessons that we learned is if you have a model, quite often the model starts on an interface level. But on the interface level, it's pretty difficult to test with user scenarios because it's rather technical, and most of the interactions that you have do not represent the user scenarios because the bad weather behavior is not bigger than the. But on top of the interface model, you can have a layer of a scenario. So if you say play the scenario, make sure that everything keeps working on the interface level. For example, if you need heartbeats to keep your session alive, keep them from happening. So you can, but actually now we're pulling that out and putting them into a thing that we more first-class citizen called scenarios, and they're more like more actually like these BDD kind of things, where you say, I have this scenario, it's an instance of a requirement, and I want to see that that has been run in the testing. 10 minutes left. Let's go to the experiences. So one of the questions that we get asked a lot, is it possible to do this? And it was also one of the questions before. They said, well, this is a system. Are you sure what you're doing? It's if you model this, it's probably one of the biggest models ever built on Earth. I don't know about that, but it's true. It's true that it's pretty big. It has several parallel processes. It has complex states. It has complex data. It has encoded or encrypted data. So there's all kinds of stuff that you need to. But yes, that's fun. And I think we're probably not unique, and that is Axini. But with the Axini platform, you have the modeling power. You have states and transitions with data and time. You can structure stuff in modules, superstates, functions, whatever. You can model configuration. So all the stuff is there to do it. And yes, the state spaces get pretty big, but it's not undoable. And sometimes you have to model it a bit different because the tool gets into a big state space that you want to prevent, and by modeling it a different way you can. And you have a couple of required features. Your models need to be, these are more the engineering kind of things. The models need to be versioned. For example, it can be in an external Git repo. That's for a lot of clients important that they have their own stuff in which they engineer. You can visualize them, you can explore them and debug them. Yeah, CI/CD integration. And those are the things that, when I said at the beginning that clients said, hey, come listen to what we need. We always thought, well, CI/CD integration, come on, it's so trivial, but for them it's a real showstopper.
It's a real necessary evil, and if you haven't got it, you're stuck.
Yeah. So they have it running. It's gated for most clients. So they say, okay, if the MDENet test fails, and almost no integration problems. And actually, this was a good for us because the project managers said most of the project managers have their problems in the integration phase, and then they were like, why does the ATIS project? Why don't you have problems? And of course, it's not only model-based testing; it's also a new project. So you try to prevent a couple of the problems that were there. We had a really good engineering team that made it. but it's well, success rubs off. So they said, oh, that's interesting. So that's also why other teams now say, oh, maybe we also want to have this. And a lot of bugs were found during development. And the interesting thing, what then happens is that managers now say, but that's bad, right? I mean, we find many bugs during development. We're like, well, no, that's where you want to have them. And because they now did it in an agile manner, they were also fixed. Most of them in the same sprint, the sprint after, and where we also have projects where we do the model-based testing basically as an acceptance test, and then only the really severe bugs get fixed, and the other ones, because everyone wants to get into production. So they go together well. So that's another thing that they learned. So basically, agile, an iterative manner of working and model-based testing. You make your models incrementally. You do the testing incrementally. You can even use it as a definition of done. The ATES team basically only had for test automation unit tests and MBT tests, and that was it. And of course, they had some manual acceptance tests, they had some performance tests, they probably also had security tests somewhere, and those kind of aspects. The modeling, well, we all know it, but to see it in practice, it really catches errors. A lot of, but it's also, I wouldn't say a problem, but when we started it, the start was tough because the modeler started modeling, or basically there was one modeler, and they started asking all kinds of questions. What does this mean? What does that mean? What does that mean? But the designer and architect was not there. They said, "Hey, why do you want me? Normally, I only get after 3-4 months I get questions." So the person was doing something else. We said, "Well, no, we 5 minutes left. Thanks." So let me wrap up, and then we can have some time for a couple of. So I showed you the ETS system, that it's basically this connectivity, well, also variability. Those are the problems. We did show that you can shift left with model-based testing. We found most of the problems during development. It's a complex system. It saved hours, so the business case was saved, but it also, the people also get back, this was actually a lot of fun to do. It was a different way of working. Some of them said, "Whoa, this is really the future of software engineering." But the slide I switched, there were also things that were hard. It was not all sunshine. And especially the start was hard, where the project manager was like, "Hey, there's no code. You're only asking questions. Where's my code?" And it was really a change that everybody, that also the designers and the architects needed to be there, and they in the beginning were not. We were even questioning why is this a relevant question? How can you now already know this question? And for them, it was really a paradigm shift. It was really, I don't like the word that much. I never see model-based development as a paradigm shift, but apparently for some it really is. The other thing that we really learned was that basically the whole team should own the models. And in the beginning, it was only this one modeler that was there for, I think, 3-4 days a week. And after a while, everybody got the training. Everybody knew how to model up to a certain degree. They all could maintain the models. Yeah, that's it.